In our last video, we discussed analytic continuation. So now I give another example of analytic continuation. Okay. So let us consider the function f1z, say f1z, and actually this is defined by 1 over I, then z minus I to the power n, and minus 1 to the power n. Okay, n equal to 0 to infinity. So at the first it may be look very odd. Okay, so this function is analytic here. How? Actually this is nothing but 1 over z. Okay, because it is 1 over z, I can write as what? 1 over z minus I plus 1. So I want to have a Taylor's expansion of this function. So it is 1 over I. So it is 1 plus z minus I by I, and if I expand it, then this is nothing but n equal to 0 to infinity minus 1 to the power n, and z minus I to the power n, and this is I, and another I was there, so it is n plus 1. So this is same as f1z. Okay, so you see that your f1z function is analytic throughout the disk, this one. Okay, so it is analytic in this domain. So it is say d1 domain. Now I consider another function, so which is integral from say 0 to infinity e to the power minus zt dt. Okay, so this function will be also analytic in some domain. So let us find this. So this is easy to find because it is a function of complex valued function having a real parameter t. So this is nothing but a real part of this and integral part of the integrand. So this I can write minus xt and minus yit dt, and that can be written as 0 to infinity e to the power minus xt, and this is cos yt, and minus I sine yt dt. So by definition we have that this is the real part e to the power minus xt cos yt dt, and minus I times the imaginary part. What is the imaginary part? E to the power minus xt and sine yt dt. Okay, so dt. Now you see that this you can evaluate. This is nothing but actually Laplace transformation of what? Cos of yt. And in the Laplace transformation we have usually e to the power minus st, but instead of s I have x, and this is the y. Okay, so and we know that this has the Laplace transformation, and that Laplace transformation converts this. What is the value of this Laplace transformation? And that is nothing but what? Your x, that means s, and x square plus y square, because I know that Laplace transformation of cos of wt or omega t, this was what? S by s square plus omega square. Similarly, Laplace transformation of sine of omega t, if you remember, then you will see that this is omega by s square plus omega square, and this exists, this Laplace transformation exists when your s is greater than 0. Okay, so s is greater than 0. So here for x greater than 0, this Laplace transformation exists, and that is the value, and this is I, and because it is Laplace transformation of sine of yt, so I have y by x square plus y square, and this is valid for x greater than 0. So I see that this is nothing but x minus iy, and this is x square plus y square, and that is it is your z conjugate, and this is modulus of z square, so it is z and z conjugate, and that is equal to 1 over z. And when it is 1 over z? When x is greater than 0, that means real of z is greater than 0. So therefore your f2 function f2z 0 to infinity e to the power minus zt dt, this is actually 1 over z when this real of z is greater than 0. Okay, so this is nothing but 1 over z for real z greater than 0. So therefore this f2z, this function is analytic throughout the region right half plane, right, real of z is greater than 0. And what was the other function f1z? Your f1z was analytic in this z minus I less than 1. So this was your d1, and what is this? This is your d2. d2 is what? Your real of z is greater than 0. So you see that in the common region, d1 and d2 in the intersection, both the functions are same, because the other function is 1 over z, and here also it is 1 over z. For real of z greater than 0, we have this. So therefore in this common region it is same. All right. So and f1z is analytic in d1, f2z is analytic in d2, and in the common region both the functions are same. So therefore your f1 is an analytic continuation of f2 into the domain what? Into d2. Okay, and vice versa. You can say in vice versa. That means your f2 is an analytic continuation of f1 into the domain d1. Okay, so that gives an example.